Hello friends, welcome again to my home. Today we are going to be learning something new, what I'm calling the second half of calculus. And we're going to start that by introducing a new kind of problem. Which we're going to start by introducing an old kind of problem. So if a car is driving at 50 miles per hour for 2 hours, how far has it gone? Now, you've probably seen a problem like this before. Maybe tens, maybe hundreds of times. If you are practicing for the SAT, you're probably seeing it a lot right now. And the way we do that is with this relationship up here, knowing that distance is equal to the rate times time. So if we want how far has it gone, the distance, we take its rate, 50 miles per hour, we multiply by the time, 2 hours. Low dimensional analysis convinces us that this is going to be 100 miles. Pretty easy, pretty straightforward. But what if the rate is not constant? So this would model more closely the situation that you are in when you're in an actual car. Like most people, except on the highway, are not going at a constant rate. Even on the highway, if you were on the highway, you might start, near, but you might have to slow down for a period, and then maybe you get a little bit too fast, and then you bring it back down, and you bring it down some more for some reason, and then you get off the highway, right? And so we're questioning, like, okay, if all we know is the speed and the time, we know something about this changing speed, how do you figure out the distance then? Well, one solution is with what's called sampling. So the idea is that rather than think about everything all at once, we just take the speed at different points. So let's imagine we did that. Now we have our situation here, right? We had an 8-hour car ride, which I know is a lot. And we have these sample times and sample speeds. And so for each of them, we have an interval of time, right? So from here to here, that's 1 hour. And then from here to here, that's 2 hours. Then from here to here, that's again 2 hours. Here to here, that's 3 hours. And so on each of these intervals, from 0 to 1, from 1 to 3, from 3 to 5, from 5 to 8, we can use our same relationship of distance equals rate times time, right? Because we have all the rates. But there's a question. Which do we use? We use, for this first interval, do we use the 40 or do we use the 30? So there's kind of a natural split where we could say, oh, well, for each interval, we can just use the number that's on the left, right? We call this the left sum. The reason is on each one, so we'll take 40 times the time, which is 1. And then we're going to take 30 times the time interval, which is 2. We're going to take 60 times the time interval, which is also 2. And we're going to take 45 times the time interval, which is 3. So this is the left. And it's called the left sum because when you do each of these, 40, 60, 120, 45 times 3, 90, 135. When you want to find what it is altogether, we add 100, 220, 355. 355 miles. So that is the left sum. But we could also take the right sum. We're using the same intervals as before, But rather than using the speed on the left, we use the speed on the right. So for the first one, it'd be 30 times 1. And then we would have 60 times 2. And then we would have 45 times 2. And then 35 times 3. So that would be 30, 120, 90, and 35 times 3, 70, 105. Add these all up. Let's see, 150, 240, 345 miles. So we have two pretty good estimations. We know that this car, barring something crazy happening, had to be going somewhere around 355, 345 miles, right? And that is the difference between the left sum or the right sum. Now, in your book, these are called LRAM and RRAM. Forgot about ARM. And the reason that they're doing that is because the RAM in each of those stands for a rectangular area method. So, if you were to take those points and put them on a graph, which I did, the method we did where we take the time interval and multiply it by the speed, that makes the area of rectangles. So if we did the left RAM, we go on the left side, so from 40, there, and there, right? And we'd find the area using the left-hand endpoint, right? However, so that's the left, basically LRAM, we make rectangles going from the left side of each interval. And then we add up all the rectangles, right? So what does the RRAM look like? Well, the RRAM, I'm going to change our pen color to, let's say, blue. We do the same thing, except instead of using the left side, we use the right side. So RRAM, we'd take this rectangle. We would take this rectangle. We would take this rectangle. And we take this rectangle. Right? And it's not clear. It's the best approximation we can get in either way. We just know that there's like two ways of doing it. So we got the left-hand side and the right-hand side. All right, let's see how this is used, right? We have some measurements. A cart is moving with the velocity shown. Notice that this is velocity. So since it's velocity, it can go negative. That's okay, works the same. Estimate the total displacement of the cart with a left and a right sum. So the first step is going to be always finding what the interval lengths are. So this interval is going to be 2. This one's going to be 1. This one's 2. This one happens to be 3. And this one's back to 2. Right? And so if we do our left sum, we take the left-hand side from each interval, so it's going to be 5 times 2, and then 3 times 1, and then 2 times 2, negative 1 times 3, and then negative 3 times 2. You do the multiplication, so 10, 3, 4, negative 3, and negative 5, and then you add them all up. So we have negative 1, so that equals 9. And so if we look at our units here, times in second plus is meters per second, our unit here should be 9 meters of displacement. Let's do a right sum. Using the same interval, so the 2, 1, 2, 3, 2, we're going to use the right-hand side. So we have 3 times 2, we have 2 times 1, we have negative 1 times 2, we have negative 3 times 3, and we have negative 4 times 2. Do our multiplications, 6 to negative 2, negative 9, negative 8. This becomes a lot more negative. 17, negative 11. Again, meters of displacement. Kind of one and the other, but it's the best we have with our data. Moving on. Now, one of the things I did mention area methods before. So this is using those methods to estimate an area. So we're going to have some words first. A surveyor measures the distance between a straight road and a stream at certain intervals as shown below. So we have road intervals, we have our stream. Use these measurements to estimate the area of land between the stream and the road. Okay, let's actually draw a picture for this. So to start off, we're going to draw our picture. And so we have our road, and it's a straight road. We're just going to draw it like this. We have our stream, and we measure every 10 meters. So 0, 10, 20, 30, 40, 50, 60, and 70. Right? And then we have a stream up here, which goes between 75, as low as 67, and as high as 84. So it starts at 75 and goes up some. I'm not going to be too careful about the scale here. Goes down some, and then kind of finishes there. So this is approximately what our stream is. And we are measuring each here. To try to find this area here, this area between the road and the stream. And we can estimate it again using a left sum and a right sum. So for our left sum, we were going, we look through and we make sure we check all of our intervals, and they're all 10, which makes things a lot nicer. So for our left sum, it's going to be 75 times 10, and then 81 times 10, and 84 times 10, and 76 times 10, and 67 times 10, and 68 times 10, and 69 times 10, and not the last one because we're at the end. You multiply all these and then add them up. Add them all up. And you get 5,200. This would be square meters, because it's meters times meters. Interestingly enough, in this case, since all the intervals are the same length, when we do our right sum, we don't actually have to do this multiplication first. Since we're multiplying everything by 10 anyways, we can factor out that 10 and do the multiplication, do the addition first. So 81 plus 84 plus 76 plus 67 plus 68 plus 69 plus 72. And then everything gets multiplied by 10 anyways, so we just do that first and then multiply the result by 10. So if you do that, you'll get 517, which you'll then multiply by 10 to get 5,170 meters squared. So this, seems like a much better estimate, and it's certainly one of the better estimates we can get just using the data itself. In the next lesson, we'll go over ways to refine our estimates with the data we have. But thanks for stopping by.